I am Daisy, and I will be the webinar moderator. Welcome to the 18th Masterclass Series webinar of the OMS eLearning Academy. Today's webinar topic is From POC to POV, Unlocking Value in Analyzer-Less Fuel Blending. We have an overwhelming response from many countries, and we welcome you all. And hope you all will have a very informational and interactive session today. Before we start, let me discuss a few house rules. The webinar will be 40 to 45 minutes long with a 10-minute queue and a session. You can enter your question in the chat box during the presentation, which will be answered at the end. The webinar will be recorded and available on the OMS eLearning Academy website. There will be a 2-question poll at the end for your input. Please give us your candid feedback at the end via the redirected Google form. In this session, you will learn about 3 essential concepts that form the foundation of this transition. First, we'll explore the evolution of blending systems across refineries, ranging from manual setups to fully automated systems. We'll then introduce the concept of analyzer-less blending, a patented innovation developed by OMS, designed to operate without online analyzers. Second, we'll define POC proof of concept and POV proof of value in the context of analyzer-less blending, supported by a real-world case study from a Latin American refinery. Finally, and most importantly, we'll discuss the critical role of clean, structured, and validated data. You'll see how robust data practices are not just useful, but absolutely essential to move from POC to POV in an analyzer-less blending system. We have 2 speakers in today's webinar. First is Dr. Suresh Agrawal, the founder and CEO of Offsite Management Systems, LLC, and Academy Director of OMS eLearning Academy. The second speaker is Francisco Trepalacios, Director of Business Development at Offsite Management Systems, LLC. I welcome them both to speak at this educational free webinar. About the hosts organizations, Offsite Management Systems, LLC, was founded in 1998 in Houston, Texas. It's chartered to provide consulting and refinery automation project executions worldwide. OMS eLearning Academy was founded in 2018 to provide continuing education to professionals working in the downstream refining industry and related businesses via the eLearning platform. Thank you all for attending this informative webinar. To appreciate your efforts, we have 2 complimentary gifts for you. Please stay until the end to learn about them. With this, let me request our first speaker, Dr. Agrawal, to start the webinar, followed by Francisco Trepalacios. I will be back at the end of the presentation. Thank you.
Greetings, everybody, and thank you for attending this useful and very informative webinar. Before I start, just want to inform you that this technology that we are presenting and discussing today in this webinar is patent pending. So I will discourage you to make copies or distribute it without our permission. Just a side note. Thank you. Now, today's agenda, we will talk about POC and POV. Now, we all have heard these 2 terms in different contexts. POC is a proof of concept and POV is a proof of value. And we'll talk about these 2 concepts with reference to why analyzer-less blending is feasible now. It's a new technology, and we'll talk about the reasons why this technology have evolved over the time, actually last 2 years, initiated by OMS. And then we'll talk about how did we go from POC to POV for a real case study that we did for Latin American refinery. How we did the model validation and how did we do the bias correction to train the model online in real time. And the model learns as the mode blends are executed. We'll give you some results and case insights, and we'll also give a roadmap for deployment for any refinery using this technology. And then we'll open the floor for question and answer. So to define what is POC, in general, a POC is a feasibility experiment to prove an idea, whether can it work technically. It's to conduct in a very controlled and limited environment like lab data, historical data, Excel, Python-based test, and it focuses only one question to answer. Can we predict blend quality accurately without online analyzers? And this question may be asked for different concepts for different technologies. But in our case of analyzer-less blending, we ask this question. Now, the characteristics of POC that if it uses offline model development like artificial intelligence, machine learning, ratio linear, first principle blend models, etc. It does the backcast versus historical lab data, typically one blend or one period of data. And the key thing in this thing, which we'll learn later in the webinar, is the historical data, how good the data is and how long is the data. And that's a critical issue for this POC to be successful. The next one comes the POV, the proof of value. Now in POC, we have proven the technology works. But the question comes, can it be commercialized? Does it have any value to it? And sometimes the POC fails to deliver the POV. Technically it's good, but commercially it does not have any commercial financial value. So it's a real world validation that the solution delivers measurable business value. Is conducted in production or pilot plant conditions and focuses on answering, does this analyzer-less blending work reliably over time with operational data? What does it really have a characteristics? It's a continuous or multi-batch testing, bias correction and tracking, RMSE, which is root mean square error, and R2M prediction KPI evaluated, comparison with analyzer output and or blend lab results, supports operator adoption and control decision. So you will see POC, it proves the technology is viable. POV will prove whether it's financially viable or not. Unless these are not together, the technology fails. And we will show you in this case study that we have adopted a different approach, combining the two together. So to compare POC versus POV, just to recap, the objective of POC is a feasibility study, and POV is a business validation. Offline is done offline using Excel, Python, any other technology, and POV is really online, where you deploy the technology in the real plant and see if it works, and it gives the results, and financially, both operationally. Time horizon is a one-time off, and it's a historical data set. Now, typically, we have used about 5 years of data from the case study. And for POV, it's ongoing across multiple blends in the real operations. We have used the matrices, correlation, backcast, accuracy, and the POV is a KPI which is continuously updated, just prove this technology works in real environment. Outcome is POC proves that it can work. POV proves it does work and adds value to it. You might have seen this chart in many of our webinars, but just to create the background, why blending is so important and why OMS specializes in blending technology and talks about blending all the time. Now, in our experience, and especially my experience, we all know that blending is the operation which makes money for the refinery. I mean, they know their operation which brings money on the table for the refinery, because blend is the final product which is sold to the customer. And it makes about 75 to 80% of the crude oil. So this is the product which is sellable. So when you sell a product, either you can lose money or make money. Now, refinery have been losing money on just blending. Why, you will see later. And traditionally, refineries have been ignoring this money-making product. Typically, I saw a shift in management's attitude for the refinery. Recently, we attended a conference in Latin America, and many refiners approached us, and their one major problem was blending. They said that blending, they were losing money. So we'll talk about it more. The refinery's profit depends on fuel products to affect its 78% profit margin. They don't make too much money. There's just 78%, and even 1% loss is runs in millions. fuel blending technology complex and well advanced in last 50 plus years. But now we have seen the shift that is going towards without using analyzers for the blending. Let's take a typical system, blending system. Now, blending system is just not one module. It's integrated about 10 to 11 different kinds of sub-modules which are automated or not automated. It needs the information from lab for the analysis. It needs the tank inventory information. It needs the, which is connected by automatic tank gauging system. Then is an additive control system. It has field equipment instrumentation like control valves, flow meters and switches and other things. And then you go to DCS, which can be any. On the top of it, a advanced control system sits on it, which is 3 layers, regulatory blend control, online blend control, and offline blend control. And they all work in a sync. So, and then once the product is done, it go to, during the blending, it go to the blend header and go to the dispatch by a tank, tankers, pipeline, and trucks and rail wagons. So every step or every sub-module that you see in diagram is subject to automation. If, for example, if the tank farm does not have a automatic tank gauging system, it's a manual label type of measuring where the operator goes to the top of the tank and downs the dip, and and so if that is the case, the blending will not be automated because it has to wait the tank level, or it's a risk of overloading anything. So a perfect, fully automated blending system requires that all these 11 modules that you see are fully automated and control, monitor, and induce a copy. This thing. That's only where the refinery can control and gain the money that it has been losing over the years. And you will see more on this later in this webinar. So typically, now we focus on a golden infrastructure blending system. Now, on the left-hand side, you have a component tanks. Now, typically, component tanks should be 2. One for running the blend and one for close, which is feeding from the process units. Now, in my 40 plus years of career in this industry, I have not seen any refinery which have, or except one or two, which have 2 tanks for the blending configuration. So what happens? When you have 1 tank only for each component, and that tank is receiving the quality, the process streams and also blending, what will happen? What changes will happen? It will change the component qualities. And you cannot put the analyzers. Refinery put the analyzer at the outlet of the tanks, but it's too expensive. So they don't put it. So what happens? They make a guess. And when it make a guess, the recipe changes randomly. It doesn't control, it's not controlled by the component quality. So then it ends up quality giveaway. On header side, there is also an online analyzer installed, maybe one, which can be multiplex, which can measure the quality of the component tanks or just the header. Some refineries even don't have that one, or if they have it, it's not maintained, it's not working. So again, the same story goes, and the blend is given away, and the refinery loses the money. Then it comes to planning side. Now, to make a recipe, you have to use a robust optimizer, which takes the interactive coefficients, blend specifications, and many parameters for the blend, because it's not a simple mixing rules using Excel. But I've seen a lot of refinery with just Excel-based optimizer. Now, Excel-based optimizer doesn't use linear equations of blending. So again, the recipe downloaded to the DCS is again not optimized. So end of the this entire cycle for bulk blend, what happens is it's a cumulative effect of inaccuracy and errors at every step. It's an error in the component quality, it's error in the blend models, error in the recipe, and they all accumulate and show up in the final lab quality of the product. And surprisingly, they find we are not meeting the spec, or we're giving away the spec. If they're not meeting the spec, they have to reblend it. If they are not, if they're giving away, they lose money. So even though this is a golden infrastructure blending system, so what do we see? We see 3 areas of concern, actually 4 areas. First is the component qualities. Somehow we have to make sure that they are available in real time. Second is the quality at the header level, which is usually done by analyzer and maintained, by the refinery. And the third thing is offline and online control system. So these four components are very, very essential for refinery to not keep on losing that millions of dollars every year on the blending, but capture quite a bit of it. And we'll talk about more on this thing. So the whole this study is around how can we measure the qualities of the components in real time? What technology can we use? AI, ML models. What technology can we use to predict the quality of the header without analyzers? And this technology is all about analyzer-less blending system. So why does blending system fail to perform? We have dealt and discussed with many refineries. There are many reasons: the tank form automation, the field equipment, blend header, analyzers, blending operations, and blending control. Now, if they have analyzers installed, so they are not configured properly, they are not maintained properly, they are not modeled properly. So what happens over the time, they are just abandoned, and then they go back to the manual operations. Now, all that I'm talking about is not a fantasy, it's not fake, it's a real, this is happening in the industry today. And if you look around, talk to your industry peers, you'll find it that they are having problem with the analyzer, they are having problem with the operation, they're having problem with the control system, and at the end, it results in a giveaway. So what are the key challenges in the blending system? First, the analyzer, as I talked about it, is reliability. They suffer from drift, delay, breakdowns. Impact is you have incorrect quality feedback, off-spec blends. The component quality variability. Now, in this case study for this particular refinery, we have analyzed the component qualities, and it varies all over the place. And if it varies all over the place, when it's fed to the component tank, the quality of the component tank will also vary all over the place. And when that happens, and you don't know what the quality of tank is, your recipe will be all over the place again. And the recipe is all over the place, you cannot meet the spec or giveaway. Then tank and line contamination. This happens when you don't have the correct equipment, which is automated, like changing the line, starting the pump and switches. And again, it can result in giveaway or off-spec network. Recipe execution accuracy, how accurate your recipe is, how well you have planned it, what model you have used. Then it results in recipe violation and economic loss. Inadequate real-time monitoring. Blends, they don't have an online blend control system. They have just offline control, offline optimizer, which is again used by Excel, non-linear models, and then it's just ratio control. The recipe doesn't change over the time, and quality of the component changing. So you see, a lot of things are happening, and they miss the opportunity for corrective action. There is no correction. Isolated system. There are too many databases, lab system, DCS, historians, analyzer, and they are not together. They are not unified. The idea of digital transformation is there. People recognize it, but they don't practice it because it's too much work, and refinery don't really understand. Not all refinery, but the majority of them don't understand what's the implication of that on the blending system, and therefore the profit of the refinery as the bottom line. So relative impact on refinery margin. The highest is because isolated system. We are not talking to each other. Lab system doesn't talk very well. Tank gauging system doesn't talk very well. It's not. You can see in terms of importance, isolated system, inadequate real-time monitoring, recipe errors, and tank line contamination, supply flow variability, and then affect the refinery margin. Even 1% giveaway can cost millions of dollars per year, 1%. And I will go a little further. I said, if you lose 0.1 octane giveaway, say for example, for 100,000 barrels per day refinery, it amounts to about $30 to $40 million, which can be achieved. And the ROI is typically between 12 to 18 months at most, So rework, cost, and slope generation degrade profitability. Incorrect analyzer feedback. Now, refinery install all kinds of advanced analyzers like NII, multiplex, and other things, and but if we don't maintain your analyzers, if we don't model them frequently, the analyzers don't work. And over the years, what happens? They drift away and they are just abandoned. Poor reconciliation, unaccounted losses, and audit issues. This all affect the refinery margin. So, are the analyzers the weakest link in blending system? In our view, yes. Because it affects the giveaway, it affects the manual adjustment, delayed response or lag, calibration drift, frequent breakdowns, mismatch with lab values. So what can we do? Yes, we can use analyzer-less blending system using AI models. And this is what we proved in this case study for a Latin American refinery. So what's the difference between the two? A traditional system, as I said, uses online analyzers with the component flows. It measures the quality of the components if it is installed and multiplexed with the component exit point, or it just measures the quality of the header. Then again, we still have the problem for quality of the components. The analyzer-less blending system is there is no analyzers. What it does, it measures and predicts the quality of the header. By technology, by models, and it uses the historical data and see, can we use information available for the blending equations, the blending models, component flows, quality, etc., and it predicts it. When it predicts it, then it compares with the 10 qualities which is measured by the lab and feeds back, and it trends, tests, and predicts. So there are 3 layers or 3 steps of creating this AI model for the header qualities, which we call analyzer-less blending systems. And these qualities are predicted real time, just like you have analyzer, working analyzer at the header level. So instead of header analyzers, AI models are predicting the quality of the header in real time. So how does this analyzer-less blending work? Traditional system, it measures the quality of the product at the header. Sometimes it can measure the quality of the product of the component at the exit point. It has a risk of calibration and a drift risk, hardware-based, costly to maintain traditional system. Analyzer-less model is a models predict product qualities. It's a real-time prediction from inputs, statistical or machine learning model, software-driven, scalable, resilient, and is analyzer-less system. And the beauty is just like a well-maintained online analyzers for at the header level, it is the analyzer-less system learns as it blends more, and every time it blends, it trains itself. The model trains itself. So next time the next blend is made, it does better and better. Ultimately, over the period, maybe about a year or so, the model is so well trained that your giveaway are minimized. Now, can I say the giveaway is 0? No, it will never happen. No matter what technology you use for AI ML, because there are other uncontrollable factors which creep in. For example, the flows of the component, there may be error, there may not be calibration, the lab analysis errors, human errors. So there are so many factors. But even 0.1 reduction in giveaway for octane turns into millions. So it's worth the exploration of this technology. And that's what we have proven in this case study. So again, a difference between the two systems, the analyzer-less blending uses historical data. It has to have a data, and the better data that you have, the better models are created and developed. Component property, that's the biggest factor. We all have it, and I'll talk about a little bit more on that one. AI or linear blending models trained on past blends, live feed, data feed from DCS, process historians, and we can have the bias stabilization logic using a lab tag and feedback. The benefits are there is no hardware maintenance, no calibration required. It's a very fast response, less giveaway, robust during analyze outage. Across multiple refineries of blend types and with backcasting validation. One of the biggest advantages of this thing is the crude switch. Now, if the crude switches, and if you have online analyzer which are working well, you have to retune the online analyzers. Now, you can also use nowadays AI-based online calibration of analyzers, but this analyzer-based system, analyzer lab-based system, it tunes itself. It detects it that component quality are changing because of crude switch, and then it learns and it detects it and it corrects itself for the blend switch. So POC to POV. Now we have talk about POC. Now, then the question comes, is this POC really workable? Does it really make money for a refinery, or just a concept in theory? No, it's not a concept in theory. It works, and that was the main point of this case study that we have done. That okay, we have seen that the POC, the concept works. Now we have to translate that into value, proof of value. So we have answered the question, can the model work in theory? Using the historical data, using the testing model, different kind of calibration, correlations, you name it. But when it comes to proof of value, then what we have done, we have taken those models and we have relived them through the blending optimization. And see, these models, if I have to do correctly from the beginning, does it create a better recipe? Does it create a less giveaway? Does it give the money to us? So for example, if you're doing a manual blending operation ratio controller, and you take the cost of the profit of the from the blending product value at the cost, you say, for example, you make $10 million in this thing, but there is no optimization. So the value of this POV comes into picture that if we take the same blend, same recipe and optimize it using the blending optimizer, nonlinear models and AI and ML, how much money do we get? So instead of $10 million, if we get $15 million profit, that's $5 million is the POV for your proof of concept. And that's what we have done in case study. We have integrated two together, POC plus POV, to show not only works, but creates the value for it. Now, for that, we have to have a concept of native model plus the optimum model. Now, what does the native model means? Native model means it's just equations and formula and model. So for example, it could be quality of the blend at the header level would be a linear equation or multiple regression equation, and where we fit the values of the qualities and the flow, and it gives a prediction. Okay, it does not optimize. It does not do anything. It just gives a prediction. Now we compare that prediction with the lab value of the same blend. And that is a native model. It means we have not done anything. So we have created 5 models, native models, and you will see later in the slides. And then we have proven that the native models, just by using the AI and ML and first principle blending model, the recipe changes, it optimizes, and it gives a better closure to the lab values. Now, that is not the end of it. Then we go to the optimized model. It means we take the same native models and we put the optimizer on it and say, okay, let's optimize each of these recipes using the same model and see what happens. When we did that, then we found the value has increased. The proof of value has increased. So the native model gave us a $10 million, but when we optimize the model for the same blend, we got $15 million. So the $5 million is your proof of value. So we have done this exercise for all the models that we have developed and using a optimizer. Now, we'll go a little bit more in detail on this concept. So we have investigated 5 types of model. The bias linear, it means the traditionally what is used in most of the refineries, where they just use Excel and linear models calculations. Then we have done that we took the same linear model, optimize it. It's called optimum linear model. And then we see how much does it give us the POV. Then we have done AI and ML linear models. Just take the same model and use AI based on, and this AI predicts the quality at the header level. Then we have gone traditional first principle blend model, which is, I call it a golden standard. In most of the refinery, yeah, they are using the blending equations, the models, maybe linear, non-linear, just the models, nothing else. Now we have combined the two together. We have taken the traditional FPBM models and AI models. Some qualities can be used as a linear model and some has to be used as a non-linear model. So we have combined them together. And when we did that, we found we got even better results. Instead of say $15 million, we got $20 million as a POV. So our profit increases from left to right as we become the more better prediction using the machine learning, AI, and the physics of the model, of the blending model. So from component to product tank, we start with linear blend models, which has as input all component tank, process streams, process stream flow rate, tech volume, etc., and then integrates it and predicts it. Now, we have also done the prediction of component qualities, which is not a part of this webinar, but maybe in future, that how can we predict the qualities of component tanks using the quality of the process streams, again, which is done by a lab analysis and not continuous analyzer, and the flow meters. And we have predicted the quality of the tank in continuous basis. And it's a surprising result that we found. Once that is done and is optimized, then the model is predicts, and we predicts it and measures it against the lab qualities. And then it trends itself and then integrates in, predicts, and goes back again. So it's a continuous loop back from 1 to 3 steps. And over the years, and this is online without human intervention, it's online. So the model is predicted, is trained, is tested, and it's ready for the next one. So we have used this whole 3 steps in our case study. And see, if we deploy this in a real plant, what will it look like? And this is, and I'll tell you how complex this computation is in terms of computer time. So the roadmap for POC is we do the data collection, and Francisco will talk about the data collection, and then we do data analysis, historical data consolidation, header and product tank qualities, and customization of blend models. Now, the blend models, which is called also the first principle blend models, are very specific to each refinery because the component, because of the process, because of some of the salient features of the refinery infrastructure. So we have to customize it, each of the linear model, whether for octane, for RVP, and other thing. And they are again done online, and it regresses parameters as we blend more and more over the time. But we started with the historical data. Then it trains the linear AI model and the hybrid model and does the recipe optimization. We have used the Excel-based nonlinear optimizer, which takes each of the historical 825 blends and optimizes the blend. So what if refinery had optimized the blend, a different model, what would have happened? And then we predict the blend qualities, and then we analyze the quality giveaway. You can see the shift of the bell curve from widespread to narrow down as we optimize it and as we do a better prediction of the blend quality. And this is again from using historical data. So that was the proof of the pudding, because unless you use historical data, how would you prove this technology? We have used a very detailed procedural flow to develop AI ML model. It starts with the backcasting, it starts with the component qualities, and it goes to 11 steps, and it calculates the average bias, bias RMSE, which is root mean square error, and the bias convention, and then goes back again for next iteration. So even for the same blend, for the same model, we have to reiterate until the bias is stabilized, until the RMSE is stabilized. And we have seen the pattern that during the iteration of the same model or same blend, it stabilizes over the time, and that becomes our stable bias. And we have done this for each of the blend model for each of the 825 blend that we had in this study. Now, what's the financial impact? Now, typically, you will think that my financial impact is gross profit and loss. I know the price of the product that I sell, I know the cost of my component, and the difference between the two is my profit loss. Yes and no. It gives you only one factor of your earning, which is profit. What happens if you lose the quality, if you give away or you violate losses, which you reblend it? That is also have to be incorporated in your profit and loss, which is on the book, the financial corporate book. They don't consider that. They just put only gross profit loss, and they say, okay, either we lost money or made less money. But in a true blending system, we have to take the cost of giveaway and a violation. So in this study, we have taken three factors. We have taken maximum profit, which is the traditional, and then we say, okay, we say what will happen if I just minimize giveaway. And traditionally, a planner, he plans the recipe based on the maximum profit scenario. When he goes to refinery level, the control engineer or refinery control engineer goes to the blend minimum giveaway, because his role is, I want to minimize my giveaway. I don't want to be become a red mark on my performance review that, hey, you lose money on the blending. Now, what if we give the best of two worlds, the planner and the blending engineer? We say, okay, we'll optimize your blend on maximum profit plus minimum giveaway. Now, that concept is very much proposed by OMS and proven that how do we do that, maximum profit and minimum giveaway. And we have optimized all our blends, all our case study blend by using all the three methods and see the profit. And surprisingly, we found maximum profit plus minimum giveaway gives you the maximum revenue, maximum benefit of the blending system. And we have used this equation just for your reference. Equations are taking care of the blending giveaway cost, blending violation cost, and minimum giveaway cost. Now, you know the price of the product that you're selling for, and you know the cost of the component. Roughly, I mean, that also is an uncertain point. How do you know the cost of the component? And there are different technology and different mathematics formulation for that one. Then cost of the giveaway. How much are you losing when you give away quality? How much are you losing when you do the violation? So all these quality costs have a certain methodology, certain this thing, and that discussing out of this scope of this webinar. But all these factors that you see here, each cost have a method to determine them and verify them, and then we'll use those things in this case study. So maximum profit, primary goal is profit margin, blend margin of profit. This is what goes in your balance sheet in the corporate book. And this is a much simpler revenue this thing, but you can also take the cost of the blend components. And if you're working for refinery, to know the estimate, know the cost of the blend components, which is coming process is not easy. Accountants and other things do a lot of calculations and this thing. We have also devised a method by which those costs of the components can be backtracked from the historical data, and there are different approaches. Then you go to minimum giveaway. Now at that point, which is at the refinery level, the goal is only minimize excess quality above required specification. Say, for example, if your octane is 84 specification, your approach is that I go as close as 83.9, 82.8. And that's as a control engineer, that's my only goal. Whether he makes money or not is not important, from my point of view, but I want to make it minimize. Then the person comes, is okay, who thinks like a planner, who thinks like a blend control engineer. He says, okay, I want to have best of both worlds. So we balance profit maximization with giveaway reduction. And we combine both equation mathematically and optimize it. And we come up with a better result, giving best of both worlds. So how did we do it? For this case study, we developed a very sophisticated Excel-based blend optimizer, Excel and Python-based optimizer, which takes many parameters. Either you can and you can control which model to use, whether you're doing a single blend optimization or multi-blend optimization, what kind of a profit margin, what kind of objective function you have, And you can manipulate all these things, and all that data is coming from historical data, or all those thousands of blends, and it optimizes. And optimization takes very fast. It's only 15 to 20 seconds per blend, and you can see that we control this. I call it a control optimizer control room, blend optimizer control room, where you can specify that what kind of a model I want to use, whether I want to use a single blend optimization, like I want to use optimal hybrid model, what kind of architecture I'm using, integrated SLP and AI, successive linear programming and AI, and whether I want to use all the three options together or multiple. Now, this is where a true control engineer or operator at the console in refinery will configure this thing, or even a planner will configure this thing. You can optimize bulk, like 825 blends, or you can do one at a time, or you can plan a new blend, or you can do what if a study simulation, all kind of thing. So this interface gives all the options available. Refinery. Now, this is only the concept. In a sense, it's based on Excel based and Python based. We are in the process of converting this to a web-based system where Excel is not a system which can be used in a plant environment. So RMSE is developing the web-based system to do the same thing. So historization of KPI analysis. Once we have stabilized blend AL, ML, FEL models, and we give the optimization option, then we can use the blend bulk optimization, and we historizer, and we do the KPI analyzer. Now, give you an idea, we have 825 blends, and we have each blend takes 35 seconds, and we have three options of the optimization. It takes about 20 to 25 hours of computer time continuously, and it is only because we wanted to use produce a KPI for all the historical blend and all this POC and POV. And so it was quite a task for five blend models and three options and 825 blends. So you can appreciate the effort that has gone into this POC and POV together. So this is another view of validation. So we take the ratio and we take the quality and we do model development, and we are feeding 4 or 5 models to do the development. And once they are developed, then we do the head of quality prediction, which is analyzer less. Then we do the final quality prediction of the tank, and then we compare the RMSE, the lab and the prediction, and then we create a KPI matrix. Now the base RMSE is the spec minus the lab quality, and the model is the lab quality minus prediction. So it's a different view how you look at it. But we have compared this RMSE for all the models for all the options, and the results are fantastic. Now you can see the RMSE of native and optimal model. Now, typically the orange bar that you see, you should be lower than all the other bars. But sometimes this data has some issue. But look at the typical qualities, which is RON and RVP. We did D50 and we did sulfur. So if you look at the orange bar, which is the hybrid model using AI and principle, that gives the maximum value. It means the POV works well. Now you see some of this benzene aromatics which is out. It's a lot of problem with the data collection and data cleaning steps. Then we have analyzed benefits per year on a basis, and for RON, RVP, D50, and sulfur, they consistently have produced a fantastic result. And we have shown that it's about a 70 to 80% improvement in the tangible benefits. It means if you have lost $20 million, you will lose $5 million because of this technology. So the gain is $15 million. Now I will hand over this next few slides to Francisco, who will talk about data collection and issues with the data. Francisco, you're on.
Okay, thank you, Dr. Suresh. Well, we have seen the potential value of this that can be achieved from this type of fuel blending system. But to accomplish this, we must work with different type of data. we have to work with the operational blending data. We have to work with the component and stream data, the lab and sampling data, and of course, commercial and operational data. But this data must be clean, complete, and consistent in order to have a good POV. Okay, next, please. So we have with this type of analyzer-less blending system, as other AI solutions that is data-driven, we use rigorous data reconciliation and optimization tools that faces two main challenge. There is operational barriers associated with data handling and difficulties associated with data structure. We are going to talk about each one of these, and also some additional challenge associated with project team and management that became a barrier to the success of the POV. Next, please. Next. Yeah, so part of this data handling challenge are the limitation to extract historical data from diverse system or database, and the lack of synchronization between this table or database that were not prepared to be looked at as a whole complete system. And this also tackles the many operational data and actions and procedures that were not recorded in a digital manner. So talking about the other challenge, so regarding the data structure difficulties that we may mention in the next slide, please. There were different format and conventions of the data, and connection between system and database, missing or invalid quality data. In general, there was not really a standard registration of all the blend information. So this all became a very big challenge to the POV. But what have we done? Next, please. So for this reason, one of the biggest efforts to carry out the POV was the preparation of the data for modeling, which involved mainly 4 steps. The first step was to unify labels in one specific language, and then cleaning and normalize the information of the data. And third, synchronize this normalized data. So at the end, we could integrate the dataset source books. There were more than 25 in a unified master data set to really start to modeling and try the different models that Dr. Sure just mentioned. Next, please. So we can say that data readiness for a blending AI application, we have to focus in 4 areas. First, localization, which is standardized the file, or the data and the language that is being used. Sanitization, where we have to delete all the outliers and normalize and make more consistent the data. And of course, the synchronization of all the historical data. The last area is we have to learn about the configuration and the specification of the system we are working with. So these are the main areas we have to prepare data to the modeling that we want to use. In general, this requires governance to establish some rules and responsibles for the data quality and validation, which is a key to this type of solution. Next, please. Additionally, I want to talk about non-technical aspect that became also an important challenge to the POV success. Was the barrier that arose in the relationship, the interaction between the working groups. First, some misunderstanding occurred due to gaps in the communications. The difference between in cultures and mindsets also prevent to have better teamwork and collaboration. And the handling of this type of project, we cannot use conventional project management, but these are more technology development projects. So when you try to use conventional project management, it arose made some tense relationship between the group. But at the end, we were able to convey all this difficulty and got a final POV with very important value to show. That's it. You may continue, Dr. Suresh.
Okay, thank you, Francisco. So what have we demonstrated in this webinar? We have shown and discussed that analyzer-less blending is viable using predictive models. POC is not same as POV, and we have to move from POC to POV to see what's the financial value to the corporation. And that's a bigger challenge. It requires a clean data, operator trust, and a bias correction. It has unified and structured data is critical for our success. So what it takes to succeed, it takes a high quality structured blend data, and it needs a number of years. We recommend at least 3 to 5 years clean data. So we're talking about 1,000 to 1,500 blends. Biased tuning during the post-blend results, operator acceptance and integration with workflows, and tools to track KPIs and validate performance. And that's a key thing. So these are the 4 factors. So going forward, our focus area is to clean and unify blend data, develop and compare multiple models, optimize the recipe using linear programs and SLP success program and nonlinear programs, deploy POV on a test blends, which validates the tank lab and economic KPI, and monitor and improve continuously, which is where the AI and machine learning and FPVM concept comes into picture. So the final thought, POC proves your model works, but POV proves that your model adds value to it. The journey from POC to POV for our case study. POC proves the model works offline, POV proves the model creates value in the operation, and POV needs validated data, bias feedback, and user trust.
Dr. Agrawal and Francisco Tres-Palacios, thank you for sharing this incredible knowledge with OMS eLearning Academy learners. We look forward to many such webinars in the future. We will now begin the question and answer session. You can email us any more questions at the email address below and the ones you posted in the conversation. We will ask you 2 poll questions with single and multiple choices for candid comments following the Q&A session. Would you kindly take a moment to respond to 2 multiple choice questions? First, what is the biggest barrier in your refinery to adopting the analyzer-less blending? Second, where do you think the analyzer-less blending system adds the most value? We will now begin the poll. We will close the poll now. Thanks for participating in the poll. Your answers will give us insight into our webinar content. Our complimentary gift is an ebook with 250 plus pages after you complete the survey. We provide a free 1-hour consultation with our academic director, the webinar host, Dr. Suresh Agrawal. Please take advantage of this chance to talk to him about any problems you are having in your refinery. or how to sign up with our academy to receive the benefits of e-learning. We have now concluded our presentation for Webinar-18. Our academy has offered monthly webinars on fascinating subjects related to downstream refining operations. Our next webinar in the series will be the journey of oil loss from the flow meters to the tank levels, the 19th webinar in the Master Series, which Dr. Agrello, OMS, and Dr. Roberto Linares of Orion Smart Solutions will present on November 20th, 2025. Refineries manage hundreds of tanks and billions of dollars in liquid hydrocarbon assets. Any imbalance, from inaccurate flow meters to poor inventory reconciliation, directly impacts financial performance and regulatory compliance. This session will explore the critical path of oil loss tracking across the entire hydrocarbon management chain, from flow meters, pipeline transfers, blending, to final tank levels. Remember to set up an account on LinkedIn. We are beginning registration on LinkedIn on November 1st, 2025. The recording of today's webinar will be available on our Academy website in a few days for you to review again. When you exit the webinar, it will lead you to the Google survey form, where you may provide us with insightful comments. We hope to see you at the upcoming webinar. Please register for our next webinar, The Journey of Oil Loss from the Flow Meters to the Tank Levels, on November 20th, 2025, at 11 a.m. CDT, as it will be posted on LinkedIn in a few days. If you need more information, you can contact via email or call. Enjoy the rest of your day and look forward to seeing you at the next webinar.
Thank you, everybody. I appreciate your attention and hope to see you next time. Goodbye.